So far up to this point in electric circuits, we've talked Ohm's law in several different circumstances. We've talked voltage, current, and resistance. And we've decided or defined Ohm's law as voltage equals current times resistance. Today, this lecture is going to go over what voltage, current, and resistance are, and giving you ways in which you can kind of make sense of what's going on within a circuit. But first, a quick review. We studied electrostatics first. Electrostatics. It means a charge on an object is static, meaning it is not moving or flowing. When we charged the balloon by friction, and we placed it near a wall, we could polarize the wall. That there's forces generated from unmoving charge. Objects can have either a positive or negative charge. That's it. And we know that like charges repel and opposite charges attract. That a force is created between the charges, and this is what we defined as Coulomb's law. We said that an electric force equals constant times charge of particle 1 times charge of particle 2 divided by some distance squared. So we determined that there were three ways that we could charge an object. We decided that charging by friction, we can charge by contact, and we can charge by induction. So what is electric current? Well, current is the movement of electric charge, or the flow of charge. Current flows when free-flowing electrons move. Right? Just as in electrostatics they were stationary, now we're putting them into motion. And we studied, or we've looked at conductors and insulators in a couple different contexts. Conductors readily allow for electrons to flow, and insulators impede or do not allow for electrons to move. Current, I, is measured in amperes, or amps, labeled with the capital A. So here we look at a circuit, and we do not see current flowing. We know that the switch is open, or the circuit is open because the switch is not linked here. We're impeding its ability for current to flow here. When the current is, or the circuit is closed, right? When I close the switch, we get current to flow and we get the light bulb turned on. That really, light is just an indicator, or light bulb, that current is flowing. So why does current flow? Well, electric current only flows when there is a difference in energy between 2 points in a circuit. Just as water flows downhill from a high gravitational potential to a low gravitational potential energy, current flows from high electrical potential energy to low electrical potential energy. And this is what we create from the voltage within a battery. So handling a wet hairdryer can be like sticking your fingers into a live socket or an outlet. The current in the outlet is able to be pushed through you, doing damage to your own electrical circuitry. But when we look at this bird standing on a high voltage wire, the bird can stand harmlessly on one wire of very high potential, but it better not grab onto a neighboring wire. You might say, well, why is that? Well, there is no electric potential difference while the bird's feet are on the wire. Therefore, it cannot push current through the bird. There's no voltage, there's no difference, there's no potential differential, so there's no current going to flow. It's current that was what does damage to people. Current is what kills, and even tiny amounts of current, right, tiny values of amperes can be damaging. 1,000th of an amp can be felt, 5,000th can be painful. In this case, 100th of an amp can lead to involuntary muscle contractions or spasms. And we can say 15,000th of an amp can lead to a loss of muscle control. And lastly, 700ths of an amp can potentially be fatal. It can disrupt your heart's ability to pump blood through your body. So the tiniest amounts of current can do damage to the body. So which way does current flow? Well, Benjamin Franklin developed the idea of electric current. He was the first to use the terms positive and negative to describe charge. We define current as flowing from positive to negative, or cathode to anode, even though we know the direction in which electrons move in a circuit is from negative to positive, or anode to cathode. So were physicists wrong? Well, kind of, but it was more of an incomplete picture at the time. If we look here, we'd see that the picture indicates flow from cathode to anode, right? We know this, but electrons actually move from anode to cathode. So what is right and what is wrong? Well, when current was first named, it was in the mid-1800s, nearly 50 years prior to understanding the electron. That electrons move from anode to cathode, and that is correct. But the reason might be a little bit different for why we see these two different directions of current in one direction and electrons in another direction. And it's the concept of why we see spokes on a car moving forward, but yet we see the spokes on it moving in the opposite direction. And this process is actually called the stroboscopic effect, and you can watch these videos. I'll load them for you to view. But it's the same concept. We know a car is moving forward, but the spokes actually appear to be moving backwards. So moving on, what is voltage? Voltage measures the difference in electrical potential energy between 2 points in a circuit. Think of this like height of measuring the difference of gravitational potential energy. Voltage, or electrical potential energy, is measured in volts. A difference in voltage is required for current to flow. It means there is energy to do work. And here's a cross-section of a battery, and I don't want to dwell on it, but just realize that it's designed to have a chemistry take place in here so that you get a chemical, let's just say a potential difference. You have your cathode up here, your positive terminal, and you have your anode down here, your negative terminal. And these are really just different materials that actually allow you to have a positive and a negative location within the battery itself. So what is happening within the battery? Well, we're creating a difference in voltage. A battery uses chemical energy to create a voltage difference between its two terminals. So if I look at this system right here, I want you to see that the picture here shows the blue guys are measuring the current, and they're carrying energy. But they use that energy to keep the bulb lit, right? We have to heat the filament within the bulb, and it lights up, gives off light. And the current still returns, it just doesn't have energy to do work. And then as it walks up these little staircase here, it's filling back with chemical energy to go back and do work. So we have this circuit here. It's based on what is taking place within the chemical energy within the battery. We often think of a battery as dying, but a battery doesn't die. It just means it loses its differential of chemical energy from its cathode to its anode. So it doesn't have an ability to push current that has energy. So what is voltage? Well, if I look at this tube here, this tube, and I say we have water inside here. So water here, there's no height difference, so no water flows. Just like if there's no voltage on a circuit, this bulb won't come on. But as soon as you lift up one side of this little tube here, the water has energy to flow. It's got a height difference, and the height difference is what we call gravitational potential, right? If this is higher, this water is going to flow. If it's even much higher, the water is going to flow even faster. We would say it has more current. And if it's just barely above the ground here, it would just kind of flow slowly. It would have a little bit of current. Well, it's the same concept of putting a battery here, right? A 1.5 volt battery here provides voltage so charges can flow. That it's the change in height that causes water to flow in a pipe. That current flows in a circuit because a battery creates a voltage difference, and that's the key here. And be sure to watch this video, it kind of goes over it as well. So what is resistance? Well, resistance is a measure of how strongly a wire or other object resists current flowing through it. Resistance, capital R, is measured in ohms by the symbol omega. Think of the relationship between resistance and current like water flowing from a bottle. The relationship is inverse, where voltage equals current times resistance is what we've defined as Ohm's law. By doubling the resistance, one has half the current. So let's look at this picture. Water's pouring out of these jugs. Here we have high resistance to water flow, right? It's got a small opening here, so water can only flow out of here, let's just say relatively slowly. So if I have a higher resistance, I have less current, if I'm looking at the water moving as my current. And if I have a larger opening, right, low resistance is going to allow for more water to flow out here. Lower resistance, more current. So in this case, if I have twice the resistance, I have half the current. Here, if I have half the resistance, I'm going to have twice the current. So different materials allow current to flow through them. So conductors, current passes easily through these materials. Electrons flow freely. They have very low resistance. And metals are very good conductors. Copper, aluminum, gold, silver. These are what we essentially create our wires out of. Semiconductors have some resistance. Example, silicon. These are used in computer chips. We'll come back to this picture here in just a moment. In some materials where current cannot flow through, these are called insulators. Current does not easily pass through these materials. They block the flow of current. Electrons do not flow freely within these materials. They have a very high resistance. The example, rubber, glass, or wood. If we look at what a wire is a conductive, right, a metal surrounded by an insulator, generally plastic or rubber. In this case, a wire is actually both a conductor and an insulator. We want current flowing through the wire, but we want to make sure that it's kind of trapped within here so that we don't touch it and get electrocuted, and it doesn't heat up to a point where it actually could create a fire or do damage. So when we look at what a wire is actually both a conductor from the metallic material inside that's allowing for current to flow. And you might say, well, where do the electrons come from? Well, they come from the metal themselves. So the conductors provide the electrons. The battery simply just provides the voltage that's going to push current through the wire itself. So if we look at a picture of conductors and insulators, if we say an electron is moving for electric current is made of moving electrons. Atoms stay fixed in place. But an atom in an insulator, it's essentially the electron is bound. In an insulator, the electrons are tightly bound to atoms and cannot move. Whereas an atom in a conductor here, the electron's free to move. In a conductor, some electrons come free and can move to create electric current. Since electrons are negative, they move in a direction opposite the positive current. And last but not least, some resistance of common objects. The resistance of objects varies. Electrical devices are designed with a resistance that causes the right amount, a very specific amount of current to flow when the device is connected to the proper voltage. So let's look at skin for a second. Dry skin has a resistance value of about 100,000 ohms. That's a very high resistance. That's good because it decreases the amount of current that could potentially flow through a human body. But wet skin? Well, wet skin changes things. It lowers resistance. And therefore, if we lower the resistance, the same amount of voltage can cause more current to pass through your body. And that's significant here when we look at the tiny amount of current necessary to even do damage to the body. So dry skin is a lot safer when you're around electricity, and I definitely never encourage it. But wet skin becomes very, very damaging because it decreases the amount of resistance, therefore increases the amount of current.